Understanding big O complexity of using DFS for Hamiltonian circuit in Markov chains. When it comes to solving complex computational problems, it's essential to grasp the underlying algorithms and their efficiency, especially when dealing with graph-related puzzles. A prominent example is finding a Hamiltonian circuit using depth-first search, DFS, within the context of a Markov chain. This guide aims to elucidate the concept of big O complexity in such scenarios, benefiting both intermediate and advanced users seeking to deepen their understanding. Hamiltonian circuit overview. A Hamiltonian circuit in a graph is a cycle that visits each vertex exactly once and returns to the starting vertex. Identifying such a path in graphs is a classic problem in graph theory and computational mathematics, often having implications in optimization problems. Markov chains and graphs. A Markov chain is a stochastic process that transitions from one state to another, where states are usually represented as nodes in a graph, with the transitions as directed edges. The study of Hamiltonian circuits in Markov chains presents unique challenges due to the inherent stochastic nature. Using DFS to find a Hamiltonian circuit. Depth-first search, DFS, is a fundamental graph traversal technique that systematically explores paths by going as deep as possible along each branch before backtracking. When adapted to find a Hamiltonian circuit, DFS seeks to explore all potential paths until it either exhaustively tests all possibilities or confirms a valid Hamiltonian circuit. Big O complexity analysis. The big O complexity provides a measure of an algorithm's efficiency, describing the upper bound on time, or space, relative to the input size. In the case of using DFS for a Hamiltonian circuit in a Markov chain. Time complexity. The big O complexity of using DFS for detecting a Hamiltonian circuit is O, n, where n is the number of vertices. This factorial complexity stems from the need to potentially explore every permutation of the vertices to verify the existence of the circuit. Space complexity. The space complexity is also significant due to the recursion stack used by DFS, which can reach up to O, n, in depth. This demonstrates that the complexity is heavily reliant on the number of vertices. As n grows, the problem quickly becomes infeasible to tackle with brute force methods due to exponential growth in permutations. Computational considerations. When applying DFS for Hamiltonian circuits in Markov chains, it is crucial to acknowledge efficiency. The algorithm is not optimal for large graphs due to factorial time complexity. Graph characteristics. Understanding the structure of the graph and constraints can sometimes allow for optimizations or heuristics to mitigate computational demands. Alternative algorithms. For large-scale problems, consider approximate methods or constrained settings where heuristics might provide efficient solutions. In summary, while DFS provides a methodical approach to finding Hamiltonian circuits, its big O complexity highlights significant computational challenges. Advanced methods or constrained settings may be required for feasible computation in large graphs, especially when applied within diverse environments like Markov chains.